inviting me to this workshop that I'm enjoying so much. I will talk on the possible molecular nature of the X0 2866 and the ZCS 3985 states. This is a work that I have done in collaboration with Tania Brandt, Natsumi Ikeno, Lianro, Dai, and Eulogio Osset. So as you know very well, since the X3872 discovery from the invariant mass of pi Jepside done by Bell in 2003, many exotic states have been discovered and the list is increasing. So we have the first clear theta square state is the ZC because this is a charged state. So this would be composed as a minimum of C Q bar Q C bar, with Q being a new allied quark. And then recently in 2021, the 3985 has been discovered. And this is an state that can be obtained from this ZC component of tetra quark by changing the light quark by an S quark. And then we have the flavor exotic that I would talk about them today, and then the doubly charmed states. So obviously these states, they do not fit into QQ bar basic mesons. So the first question that we can ask is whether those are meson-meson molecules or theta quarks or other kind of exotic states, and how can we build the interaction. So the X0 2866 is the first flavor exotic tetra quark. It has two open quarks, one C bar and S bar. So two states indeed have been discovered, one with 0 plus and the other with 1 minus. And you can see here the picture from the LHCb. Actually, there are predictions from one of these states. If we go back to 2010, quite a long time ago, there is a work done by me, Tania Brandt, and Eulogio Osset, where we studied by the first time flavor exotic states. And as you can see here, we obtain states from D star K bar star interaction, doubly charmed states, also from D star, and from D star S, D star. So this is a summary table from that article. At that time, we did not know how to fix the free parameter. So the only state that there was around the D star K star threshold, it was the DS2 2573. So we fixed the free parameter in order to get this state. And just with one parameter, we obtain all these states. As you can see here, we get 3 states for C equal to 1 is equal to -1, that was coupled to D star K bar star. Another one that would be the spin partners of the DS2 2573, coupling to D star K star, D star S omega, and D star S phi. We get also one state for isospin equal to 1 and spin equal to 2 plus, coupling to D star S rho, and doubly charmed states. So now, knowing about this observation of the LHCb, we can somehow assign this new state to the prediction that we made in the past. So after these discoveries, many works have appeared. So, and there are different interpretations. So for example, Karliner and Rosner, they interpret the 2866 as a compact tetraquark. Then in this work, Liu and Yang, they say that this is a triangle singularity. Li Shengen and collaborators, they support the D star K bar star molecular state, while they say that the X1 cannot be a molecular state, but instead 1 and T, they claim that this is a D bar 1K molecule, where the interaction is driven by rho and omega exchange. And there are also some works saying that some of these ZCS states are just threshold effects. And Albadalejo, Guo, and Nieves, they have worked out an interaction which is energy dependent, and they show that the ZCS 3985 and ZC 3900 are likely SU3 partners. So, and we have also some works that we have seen some of them in this workshop about doubly charmed state, and a prediction from the lattice, the first extraction of a doubly charmed state. So I wanted to say here that as you can see, there are many different interpretations. So first we need somehow to clarify whether these new exotic states are molecular or compact tetraquark, and then we need to learn how to build the interaction. So in this work, I will talk about the local hidden gauge approach. The hidden gauge Lagrangians, they were introduced by Bando, Kugo, and Yamawaki. So the Lagrangian has basically these two terms. From the first term, for low moment of the meson, we can get the lowest order chiral Lagrangian for pseudoscalar mesons interacting. From the other terms, we have interaction of vector mesons with pseudoscalars and between vector mesons and also with photons. So in this picture, the photon couples by means of a vector meson to the couple of pseudoscalar. So we have the basic feature of vector meson dominance. So in order to work out the vector-vector interaction, we extract the two essential pieces. We have a 4-vector contact term and a 3-vector contact term. And then from there, we have basically the diagrams A and C and D. This has been studied by Li Shengen. It is small compared to the others, while the dominant terms are the A and C, where you can have here a vector meson exchange. In the case that we are interested now, which is the case of the exotic D star K bar star, you would have these diagrams where you can see you have like vector exchange. So this term of the interaction respects fully heavy quark spin symmetry because the heavy quark acts as an spectator, while this would be a subleading term. So we do some approximation, which is the low moment of the vector meson compared to its mass. And then when we do that, we get these spin projectors, and we can rearrange the terms in the Lagrangian in this way, so that the vector meson that appears here can be only an exchange vector meson, because if it was external, when you contract with the momenta here, then it would disappear. So then we get the interaction for isospin equal to 0 and isospin equal to 1. And as you can see, the interaction is attractive in isospin equal to 1. There is also another feature that I should comment, that in this local hidden gauge approach, we always get that the spin equal to 2 state is more bound. As you can see here, this is the full potential at the energy of the threshold. So another thing is for isospin equal to 1, the interaction is repulsive. So we don't get any states. The free parameter comes from the two Mason loop function. In this case, we have only this parameter for fixing the mass of the state. And then we solve the Salpeter equation, and we include also the possibility of the pion exchange by means of this box diagram that allows the state to decay into decay bar. However, since you have here that the initial parity is positive, then the intermediate state can have only L equal to 0 or 2. So then the spin equal to 1 state cannot decay into decay bar. So we have done recent work where what we do is we take the new observation of the LHCb and we do a fine tuning of the free parameter of the model. So we, in that work, alpha was equal to minus 1.6. So we change it to minus 1.474 and we get the state right at the right position. And then we also do one calculation, that is, we evaluate the decay width of the 1 plus state, that it would be the spin partner of the observed X0 state. So we evaluate the decay width of this state by means of this box diagram. And for this box diagram, we have the opposite. L cannot be 0, so this cannot contribute to the spin 0 state. So we make some simplification, and is that because this vertex cannot be on shell, so the imaginary part comes basically from this cut when these two particles are on shell. So when we take this into account and we work out the polarization vectors, we get that indeed this decay mode only contributes for spin equal to 1 and spin equal to 2. While for J equal to 0, it violates parity. So this is the result when we include this decay mode. So the state with J equal to 0 stays the same, while the other two states, they have gained some width. And this, you can look, we vary a little bit the lambda in the form factor. So this gives you some idea of the uncertainties that we have in the model. So this would be the result for the J equal to 1 state. So now the question becomes, how can we observe the spin equal to 1 plus a state that would be the spin partner of the X0? So if we go to this experimental paper, so there are several branching ratios from B decays were evaluated. We pick this reaction for several reasons. It is because it proceeds via external emission, and also it has the largest branching fraction. And of course, it can produce a D star plus K minus, which is the decay mode of the 1 plus state in isospin equal to 0. So then we evaluate the invariant mass distribution of this reaction. So we have the B meson, which is decaying into the bar star 0, D star plus K star minus, and then it hadronizes into the resonance with a spin equal to 1, and then it decays into D star plus K minus. So this vertex, it can occur into S wave. We assume dominance of this partial wave, and then we can write this vertex in this way. For the hadronization vertex, we need to take into account the spin equal to 1 projector. So when we sum over the polarizations of the 3-vector meson, we get a factor 6. So here you have the terms that come from the evaluation of this diagram, where this factor comes from the primary vertex. Then you have the 2-meson loop function. Then you have the hadronization and the decay, the resonance, the propagator due to the resonance, and the decay of the resonance into the star K bar. We compare the result with the background. For the background, we also assume dominance of the S wave, and this is the result. As you can see, the peak is 5 times larger than the background, so it should be seen in the experiment. And we work out also this reaction, where instead of the D bar star 0, we have now the K star 0, and we obtain a similar result. In this paper, you can also look at the production of the X0, where you would have that instead of K star 0 or D bar star 0, you would have K0 or D minus, and instead of D star plus K minus, you would have the decay mode of the X0, which is D plus K minus. So we show there that the X0 can also be seen in these reactions. So now I go to the second part of the talk, which is the hidden charm strange state. So as it was reported before in the previous talk, BES3 has reported the newest state, which is the set CS 3985 from the invariant mass distribution of E plus E minus going to K plus and this combination. So this state is around 7 MeV above threshold, and it could be the SU3 partner of the set C state, just changing by U or the quark by an S quark. So using the hidden gauge formalism, we take into account these 4 channels, F psi K minus K star minus eta C, and D star is D bar 0, and then we build the interaction. So as you can see here, it is not possible to exchange a light vector meson, only heavy vector meson is possible. So in this sense, the interaction becomes much weaker than in the other cases. For example, for the D star K bar star. And by analogy with the set C3900, where you have 2 states with G parity positive or G parity negative, we build these 2 combinations. So, and we see that indeed the combination A, it couples to F psi K minus, K star minus eta C, while B not. So in the case of the B combination, you would have only this diagonal term, that is because you have the exchange of the F psi, it leads to a very weak attraction, and it does not lead to any accumulation of strength around threshold. However, for the combination A, you get that this term is reinforced by the non-diagonal terms, and as you will see, we get some accumulation, some more attractive interaction that it is visible in the reaction. So we study the E plus E minus going to K plus and the combination, this combination of this reaction, and this is what we obtain. So here is the 2-couple channel case while the orange line is the one channel case and the dotted green is the phase space. So as you can see, only the two coupled channel leads to an accumulation of strength around threshold, and this is in agreement with the experimental data. We don't get any bounded state. What we get is a cusp or a threshold effect. And so if there are some cusps or threshold effects in the D star bar S D, so are there states in D bar star S D star? So we have done this study where we consider all the possible diagrams with vector meson. And we also include pseudoscalar exchange in order to have these possible intermediate states that would be eta C K plus Jeff psi K plus by means of box diagrams. We use two different cutoffs. So for J equal to 0 and J equal to 1, we don't get, again, enough attraction and we get nothing relevant. But for the case of spin equal to 2, we get a coupled channel to coupled channel interaction that is strong enough to be observed in the experiment. We use two different cutoffs. The cutoff used for Jeff psi K star is larger because around this energy, the momenta cannot be larger than the cutoff. So that's why we need to use a cutoff which is larger. So you have here around the threshold of D star S D bar star, there is an accumulation of strength, a peak, that can be associated with a cusp due to the coupled channel interaction. We study this mechanism that has been done by the LHCb, and this mechanism can have internal emission and also external emission. And then after this external emission, you would have an hadronization. And these are plots of the invariant mass distribution. So you can see here again that you have kind of a cusp around 4,120 MeV. And this is the result for different cutoffs that we have used in the integrals. So indeed, if we go to the paper of the LHCb, we can see that there are some hints of an accumulation of strength around 4,120 MeV that I show here in this orange plot. And this is larger than the error bar. And also notice that in this paper, where you have a different reaction, B bar 0 going to Jeff psi K minus K plus, also done by the LHCb, you can also observe around the same energy a peak. So we think that this can be associated with the cusp around the threshold of D bar star S D star. And then I go to the conclusions. So the X0 2866 is a good candidate to be at D star D bar K star molecular states. We have proposed several reactions where the spin equal to 1 plus state can be observed, the spin partner of the X0. The set CS3985 can be explained as a threshold effect from the coupled channel interaction, and there should be also another cusp corresponding to the D star S D bar star interaction with the Jeff psi K star. And we suggest to look around the data on BDKs around this energy. Okay, so thank you.
Thank you, Raquel. Any question, comments? Okay, Christoph.
Hi, Raquel, thanks a lot. I have actually one remark and one question. Let me start with the question. What I'm wondering is about the expected accuracy of your calculation. You make two, from my point of view, strong assumptions, which I would like to have your feeling for how you quantify them. The one is you use SU4. I mean, you have the same couplings in the pure SU2 stuff as well as in the SU3, SU4 stuff, which I think is not soundly rooted in QCD. And the second assumption you are making is that the binding potential does not have any one pion exchange, which I don't understand either. Therefore, given that you make those assumptions, what would you estimate on the reliability of your calculations quantitatively?
I mean, the first thing is that we calculate uncertainties. I mean, in this slide that I showed just at the beginning, here, so you can see that here we have model A and model B. So this model A and model B, actually they come from having different couplings. So in one we have this coupling and in the other we have the experimental coupling. So, and we get similar results. So it doesn't seem that to be a problem. It just, okay, we have some uncertainties that we are aware of. And then the second thing is that I think Eulogio, he has a paper with Liang showing that if you consider the vector exchange diagrams, you don't need to correct in the vertex of heavy meson, light vector meson by the coupling of with heavy vector mesons. I mean, this is.
No, that wasn't the question. The other question was the pion exchange.
Yes, and the other question was the pion exchange. Well, this is related to the pion exchange. I mean, the pion exchange is in this work is important for the decay width of the state. These box diagrams we have calculated many times, and the real part of this diagram is really small and negligible. So we don't think that it is relevant.
But do you think by just calculating that box in the kinematic constraints that you do it is really a proper estimate of including the one pion exchange in the potential? Because usually when we include the one pion exchange in the potential, we get very large contributions, and I cannot reconcile that with your statement.
Well, I think Juan Nieves, he has a work. Well, he used an effective field theory that he has contact terms and then pion exchange, and what he gets at the end is that the pion exchange is small.
Well, this is something that one still needs to discuss eventually. Thank you very much. I don't agree. That's what I wanted to say.
Okay.
Okay, thank you. Another question, comments? I don't see any. Okay, then let's thanks Raquel again and move to the next speaker.